Hey YouTube, this is Ronen, and I'll show you right now my new proof of the four-color map theorem. The four-color map theorem says that if I have a map, meaning any finite two-dimensional plane, no matter how I section that map into regions, called countries, I will always be able to color the map in with at most four colors such that any two countries touching each other will have different colors. Touching each other doesn't include two countries sharing only single points. Now I'll give a quick example and then show the proof. This is an example where I try to make a country, now it's country number 5, where this country has to be in a fifth color. And now I'll show why it doesn't work. Country number 1 touches all countries, so all other countries have to be in a different color as country number 1. Country number 2, same story. So country number 1 is color number 1, country number 2 is color number 2, country number 3 touches country number 1 and 2, so it has to be in color number 3. Country number 4 touches all of the previous countries, so it has to be color number 4, and country number 5 can be color number 3 again, so there is no problem. Country number 5 doesn't have to be in a fifth color. Now I'll prove that in all cases, in all of the maps you draw, it doesn't matter how tangled up you draw them, you can never make it so that there will be a map that has to be in a fifth color. Here's the proof. Now, country number 1 will be the country that I'm going to try to show that it can't and doesn't have to be in the fifth color. So to show that, I'll try to show how it might, yes, have to be, or it has to be in the fifth color. The only way country number 1 has to be in the fifth color is if 4 other countries at least are touching it, and each one of these 4 countries are in different colors. So you can see country number 2, 3, 4, and 5. If country 2, 3, 4, and 5 will all be in different colors, and country number 1 touches all of them, then country number 1 will have to be different than the color 2, different than the color of number 3, different than the color of number 4, and different than the color of number 5, meaning it will have to be a fifth color. So the only way these 4 countries will be in different colors is if they're connected. If they're not connected, they can just be in the same color. So right now I'll try to show how they might be able to be connected. So the countries might be able to be connected like this. 2 connects to 5, 3, and 4. 3 is already connected to 2, so it connects to 4, 5, and that's it. 4 only has to connect to 5, and is already connected to the rest, and that's it. That's all I need. Now notice that countries can't be divided into 2 separate sections. So if I have this gray country, these 2 gray sections can't be considered one gray country. So when the 3 country spreads out to connect to country number 5 using the connection I show on the board, then there's no way that it can interrupt the connection between 2 and 4. Because if it would interrupt, then the country wouldn't be one continuous country, and it wouldn't be considered to be one country. So now I'll try to show that you can't connect these 4 red countries 2, 3, 4, and 5, all to each other, without cutting through countries, which is not allowed. If I prove that, then I automatically prove that there is no orange country that has to be a fifth color. So let's start. I just chose a completely bizarre shape for the color for the country I'm trying to prove that has to have the fifth color. So, as you can see, this country has borders. It has an outside border that goes all around it, and it has two inside borders. I define borders as lines that if you go upon and don't go to the other side of them, you can just continue and get to where you started. Because if you can't go out of these lines and connect to a different border, then if you have a country that's connected to one of these borders, let's say I'll draw the countries in yellow. So I have one country here connected to this border, and one country here connected to this border. They won't be able to connect to each other. And if I have one connected to this border, it won't be able to connect to the rest of them. So I'm going to give an example of an outside border and an inside border, where all four countries are in, and show it doesn't matter if it's an outside border or an inside border, these four countries can't connect all to each other. So I'll start from an outside border. If I'll have countries all connected to the outside border, something like this, they automatically divide this border into regions. Now, I'll give these countries numbers. So, I'll do it in black. 1, 2, 3, and 4. So if I try to connect country 1 to country 3 using a pink line, it will look something like this. 1, 2, 3. It can go either from that way or from the other way. Now, if it goes from 1 to 3 in this way, it will block country number 2 from connecting to country number 4. Because if country number 2 could connect to country number 4, it means that there is no continuous line between 1 and 3. And country number 2 can come and start from right over here, continue on to search and search and search for a place to go out, and it will eventually get to the border of 3 and it will have nowhere to go out. So that means that if, no matter how I connect country number 1 to country number 3, which I will have to do eventually, I won't be able to connect country number 2 to country number 4. And if I connect it from the other side, the same thing happens where I can't connect country number 4 to country number 2, because I can't cut it in the middle. Now I'll show what happens in the inner border. Now, if I'm already dealing with countries in the inner border, I might as well add a note. The only reason that it could be impossible to connect one country to another one is if the different connection between two other countries, two other yellow countries, is blocking it. So if I reduce every single country only to a little slit of the connection point between the red country and the yellow country, as I'm doing right now, then it won't make it any harder or any less possible to connect the countries to each other. So I'm going to reduce it like that. And now I'll show that it's the same thing also over here as the outside border. So I'll give the countries names. This will be country number 1. This will be country number 2. This will be country number 3. and this will be country number 4. Now, if I try to connect country number 1 to country number 3, I'll have to go along, and I can start going aside, and I can go to the other side, but I'll always have to go above country number 2, if I go from here, and above country number 4. And no matter how I go, if it's a continuous line, and I can't go from this side because it's on the border, and I can't go from this side for the same reason, then country number 2 will be blocked from getting to country number 4. It's blocked. That means that also in the inner border and also in the outside border, any inside and outside border, it divides the border to regions, and it blocks when I try to connect one country to the opposite country, which is country number 1 to country number 3, or 4 to 2, it will block the other 2 countries from connecting to each other. That's it. I don't understand why no one used this proof. I know there is a proof using graph theory, which is basically this, but just this doesn't depend on block and graph theory, because I just reduce the yellow countries all the way instead of using a graph, and it's completely visually dependent. It's not abstract. So hope you enjoyed the video. Please comment and subscribe, and tell me what you think.